All right. Welcome back, everyone, to the monthly Ceph Tech Talk. Such hallowed halls and speakers as Sam Just and Josh Durgan used a lot of different talks on the core aspects of Ceph, but pretty much anything that's technical and has to do with Ceph is something that we're looking to host on these talks. Today we get to hear about building a Ceph reference architecture from a couple of the experts who have done just that lately. As always, if you have questions going along, feel free to type them in the chat. We can get to them at the end. If you'd like to unmute your microphone and ask questions, let's try and do that at the end. That way, folks that are following along at home from the YouTube channel can see the whole presentation before the questions start. Without further ado, though, I'd like to introduce Brent, Compton, and Kyle Bader, who are going to give you a rundown of how we build reference architectures. You guys want to take it away?
Yeah, thanks, Patrick. So Kyle and I are going to keep this interactive and conversational between us as we go along. Informal, best. So that's one of the things that we do. We spend time with a lot of our partners building reference architectures. One of the key questions, or one of the reasons we do this, is one of the questions, most frequently asked questions that we get is, hey, this software-defined storage stuff is great. It runs on anything. What do you recommend? Answering that question, of course, like you all on the phone, we'd like to answer that question based, rooted in empirical data versus on kind of hearsay. So we spend quite a bit of time in various partner labs running through a variety of different benchmarks and load tests in order to have data upon which we can base answers to questions like that. So we're just going to kind of walk through some of the things that we look at, some of the considerations that we have when doing that. I'm in full screen mode, so Patrick, I won't be able to see the chat window. So if there's anything urgent comes up in chat, just flag me, okay?
I'll let you know.
So I'm going to do this little thing here. Okay, so the building blocks for reference architectures common. Being distributed storage, of course, network is the foundational building block, and sometimes something we don't talk about enough. You know, the impacts of 10 gig. I know it's well known in the community the use of two 10 gig networks, one client facing and one cluster facing. But as you go up in network bandwidth to 40 gig, as you look at bonding or not, to bond or not to bond, makes a significant difference. And those are some of the variations. And of course, then up to server in the last probably 24 to 36 months, as you know, there's been just an explosion of variations on storage, x86 based storage servers. A couple years ago, it was kind of the default was a 12 bay, so 12 3.5-inch drive 2U dual socket server. Now there's just a litany of different storage servers out there. Just looking at capacities, 12 3.5-inch bay, 24 3.5-inch bay, 30, 36, 60, 72, 76. And so, and then of course the question that folks ask is, well, what's the what kind of performance can we expect with different server types, and let alone different media types within those servers, different capacities of HDD, obviously, lowering the capacity, increasing the quantity of servers, changes the spindle count, obviously going to change the type of performance you can expect. The classic question of SSD write journal ratio to HDD, but what about instead of a SAS or SATA SSD write journal, what about PCIe, NVMe write journal? How does that change things? And then what about putting the OSD all together? Instead of hard drives on flash drives, how does that affect things? So lots of different permutations going on at the platform level. And then on top of that, at the OS or Virt level, folks saying, okay, so what about if I'm driving this load through a KVM VM, or just driving the load through the Rados gateway, no Virt layer, or emerging, of course, are questions we're getting on from a microservices, a container type Virt level. And then on top of that, this is kind of pseudo Maslow's hierarchy of needs here, with the bottom being kind of food and shelter, working up to the self-actualization level is the defined workloads. What in the end, people are, of course, have the underlying stack to accomplish work. So some of the reference architectures, of course, would cut a cross section, a vertical cross section, starting from a defined workload and all the way down through. Others are foundational. In fact, if you look at RefArch flavors, some RefArchs read more like how-to integration guides, and these tend to be at the upper layers of that hierarchy of needs on the previous slide, where kind of Ceph layer and at the OS or Virt level, and then on top of that, Ceph plus OS Virt plus packaged workloads on top of that. An example of that is here in the link. This is a Dell Red Hat reference architecture for Red Hat Enterprise Linux OpenStack platform. So, RHEL OSP, OpenStack, plus Ceph on top of Dell PowerEdge servers. So, and that RefArch reads more like a how-to integration guide. And that's one flavor. Another flavor read more like performance and sizing guides, and listed are 3 different links there. One is a reference architecture we've recently published with Supermicro. It's across their family. The second one is a performance white paper in which we've collaborated with Cisco's UCS team. And the third one is one from Scalable Informatics, another performance white paper. So all of those read more like performance and sizing guides. So right now, as just FYI, our team is currently focused on the bottom one, the performance and sizing guides, mostly because there's just so many questions that we get peppered with about performance and sizing as the explosion of permutations of server, media, and network grows. So that's going to be kind of how we focus our comments today. That's where we've been focused with and building these reference architectures, is more the latter. We're working towards the former, the top one there. In fact, we've begun to work with the MySQL MariaDB community at the top layer of the stack. But again, a lot of our work has been foundational. So that's just kind of sets your expectation for the type of reference architectures we've been most recently involved with. Okay. By the way, I'll say right here at the beginning to the group, one of our goals with these reference architectures in producing these performance and sizing guides is to create a community asset, such that if one of you are saying, yeah, I'm deploying a new Ceph cluster, my workload IO patterns look kind of like this. My capacity, it's going to be about a petabyte or 2, and I'd like to run it on all flash, or I'd like to run it on as cheap and deep as I can go. I'd like to I'd like to go out and query some community repository to find out who has performance results from an architecture like I'm looking to build. And save me some time if I can read up on some empirical data in some type of structured form. So that's what we're working towards. If we have time at the end, I'll paste up there. We have right now it's simple. It's just a massive spreadsheet. We're close to 30 different results from 30 different configurations, and we have them all lined up side by side, so we can look down a row and see how various performance metrics varies with different configurations. So it's quite insightful. It's fascinating, in fact. So we'd like to mature that. So instead of having to be a spreadsheet jockey, it's a little bit more user friendly. But anyway. So that's a plug out. If anyone's got great ideas, funnel them through Patrick to us. We're very interested in that. Okay, so back to then talking about our considerations for these reference architectures. Okay, so performance and sizing guides, where most of our work is. Here are 3 links illustrating some recent work. Okay, so here are some design considerations that as we structure these reference architectures that we focus on. So I'm gonna focus on a couple of these. Then, in particular, again, it'll be conversation between Kyle and myself. You've probably heard Kyle on this venue before, senior storage architect from not only the Ink Tank days but the DreamHost days. Kyle will cover 5 and 6 here, but along the way we'll may ask him other things. Okay, so here are just 6. By no means is this an exhaustive list, but here's some useful design considerations that we speak about in constructing these reference architectures, and it's effectively as we speak about in taking it from the top and architecting Ceph solutions. So these items, this is meant to read, after having these conversations with, internally or with whoever the solution architects are, to understand these 6 things, 1 + 2 + 3, equals, then, building up enough data in order to design target server and network hardware architecture. That's what the line is meant to be. It's meant to be a summation line. Okay, so we're going to talk through each of these design considerations, and if we have time at the end, we pulled a few graphs from one of our performance graphs from one of our recent reference architectures. You can kind of see the variation between different configurations and how those may be affected by some of these design considerations, and how they might be more applicable to certain workloads. So anyway, if we get time at the end, it's certainly in the slides, you'll have them in the download. We'll talk through a couple of performance graphs. Okay, so number 1, first design consideration, qualified need for scale-out storage. We're not going to spend a lot of time on that here. Something that you do all the time, every day. So I'm just going to kind of leave this at that, not going to focus much on that. One interesting thing, just as a side note, ran across this graph from IDC a month or so ago. Fascinating, the trend line with storage capacity moves back into the server, away from external SAN NAS, depicted there in dark blue, it is external capacity, and back towards internal capacity. Very, very interesting 5-year moving trend. So anyway, that's just an interesting thing. So anyway, so the first design consideration, qualified need for scale-out storage. As you all know, as architects, that frankly, they're depending on the size and the if it's an Oracle database, size, workload, and whatnot, it may not in fact be the right solution. But so moving on past that. Okay, the second design consideration. Designing for the workload I/O, and this kind of sets up the way that we approach the reference architectures. We have a 4x3 matrix. It's kind of a small, medium, and large with different I/O patterns, which you'll see in a minute here. So this kind of sets that up as we look at the different considerations of the various workloads. So the first, the overall, the topmost governing factor that we see is, okay, people designing these Ceph solutions are they performance oriented or cheap and deep oriented? Cheap and deep being, their overriding interest is cost capacity, cost per capacity, cost per rack density, cost per watt, cost per thermal unit, cost, cheap and deep. Or do they have some type of performance, overriding performance objective? Of course, that cost is always a factor, but if it's an overriding performance objective, again, that's So we test different, in our reference architectures, we try to go through different configurations that will be optimal for these different types of workload patterns. And then descending within performance, certainly some, performance can be further broken down into sort of throughput oriented with a lot of digital media streaming. It might be an image, a lot of JPEG images. It may be video, audio, but anyway, large block. With the I/O pattern typified by large block I/O. In fact, large going down the list, sequential large block I/O. Versus IOPS intensive, obviously typified by, the poster child IOPS intensive workload being 4K random I/O, so small. And so all these considerations, again, we try to, in the reference architecture work, we try to say, okay, on this slide here, in this 4x3 matrix, the rows become these are very coarse-grained, generalized workload I/O categories of IOPS optimized workloads, throughput optimized workloads, and cost capacity optimized workloads. Obviously, cognizant that within a single cluster, you might have different pools carved out for different workloads, but this helps us again to identify reference architectures which are optimal for these different types of workload I/O categories. And then back up to this thing here, some of the things that become interesting down below are things like the read-write mix. As we benchmark things like erasure-coded pools versus replicated pools, as you'll see in the results, for instance, the write performance. Write performance of in an erasure-coded pool versus replicated pool, it's a different ratio than read performance, and for all the logical reasons that make sense when you think about what's going on the covers there. So a lot of these factors become relevant in identifying candidate architectures, server and network architectures, which will be used in the reference architecture benchmarking. So this is one half of the grid that we lay out again as we identify candidate architectures to test. And when we look at performance optimized, of course, as we discuss with our partners, and we work with network partners, we work with server partners, we work with media partners, and we discuss this with them as we're looking at performance optimized reference architectures, the benchmarking for that. We're say, okay, our goal here is, of course, we're trying to get in by definition performance optimized. We're shooting for the highest performance that this pool can yield. Again, whether it's megabytes per second for throughput oriented or IOPS for IOPS oriented, but clearly not in a vacuum. Cost always matters, so then it becomes, okay, we translate the lowest. We also get list pricing information for the configuration, so that we can begin to do some relative. And most vendors aren't all that. They don't like, of course, to have a lot of their absolute pricing information bandied about for obvious reasons. So we convert that into relative comparisons. And again, if we have time at the end, we have some relative comparisons that reflect lowest cost per performance unit. So yeah, sure, you could, a configuration might yield the highest performance, but it's liquid nitrogen cooled and it costs $100 million. Okay, it's nice that it's highest performance, but it's not attainable by mere mortals. So we look at some CapEx elements, as well as one of the things that Kyle drills in over and over again is from his experience on the operations side of the fence is, hey, power and cooling always matter. So yeah, you might get a cheap capex solution, but if you're burning through the Los Angeles power grid because you're sucking so many watts and air conditioning, then it's still too expensive. So we try to have the reference architectures pay consideration to that as well. And then finally is meets the minimum server fault domain recommendation. And we're going to get into that, and it's a favorite topic of Kyle, so he's going to talk to that one. We get down farther below. Okay, and then cost capacity optimized, set otherwise cheap and deep. Of course, it's the governing attribute is lowest cost per terabyte. But again, it's also a capex and opex game, so the same opex things matter here. But instead of looking at best performance per thermal unit or watt, it's in this case it's back to cost capacity optimized. It's per terabyte, and of course because some data centers pay. The payment is the OPEX cost is more oriented towards floor space, built-in floor space, then that's an important element here. And we relax a little bit the minimum server fault domain recommendation here for cost capacity optimized clusters. Again, with the belief that it's less performance sensitive. Okay, so with those considerations, then the third of 6 design considerations we look at are the obvious storage access method. This is simple and obvious. A couple of caveats that will come into play later on. Used white font, or I should say I use white font. Sorry about that. The last at the bottom, it's kind of hard to see. But for instance, obviously, Rados block device is supported with a replicated data protection scheme only. So choice of storage access method. For instance, if the storage access method required by the workload is, for instance, block, that immediately constrains the data protection scheme used to a replicated pool, which then obviously drives it constrains the permutations of server network, in particular server and media architectures targeted. So anyway, that's kind of the third design consideration. Then the fourth one, identifying capacity. And identifying capacity, at face level, one might say, well, what does that really have to do with the reference architecture? Well, it comes back to the previous slide or the previous conversation about fault domain considerations. Clearly, if you're architecting or you're designing a reference architecture for a 0.5 petabyte solution, then it's probably not going to use big old dense 72 bay servers from a fault domain perspective. So identifying the capacity has significant ramifications into the fault domain, and so that's actually a good transition. So Kyle, as we look at fault domain risk tolerance, and clearly we've termed this as risk tolerance because it's a choice. It's a subjective choice by the architect here based on the environment. So Kyle, talk to us a little bit about this question about, okay, what percentage of a cluster capacity do you want on a single node? Talk to us a little bit about that, Kyle.
Sure, absolutely. So when you have a scale-out storage system, typically you're transitioning from the mindset of where you want to, instead of trying to make sure that a singular host or a pair of hosts are highly fault tolerant within themselves, instead you want the cluster and the cluster software to provide the fault tolerance. In order for that to work properly, you need to have sufficient hosts in the cluster so that you can survive the loss of one of these hosts. In the case of a Ceph storage cluster, kind of the rule of thumb that we provide is that you don't want to lose more than a tenth of the cluster with a single node failure. Because not only are you going to lose 10% of the capacity in the case of a node failure, but you're also going to have the additional workload of having to recover from that failure. So when you start to get into clusters that are smaller than 10 nodes, and you can see how this can be very problematic, right? So if you have the absolute minimum 3-node cluster, one of those hosts fails, you lose 1/3 of your capacity, and the remaining 2 hosts have to not only is there less aggregate cluster bandwidth available, but the remaining bandwidth also has to deal with the recovery of that failed host. So based on testing that we've done, we really like to steer customers towards clusters that have a minimum of 10 nodes, for performance, and relax that a little bit for cost capacity conscious clusters.
Hey, here's another question for you, Cal, before we leave this slide. So the one of the things I know that we've talked about a lot before is also the cluster's reserve capacity in terms of terabytes. So there's a certain amount of reserve that you should always have just for normal operations. But then let's say that you have a 3-node cluster. How does that reserve capacity need to grow when you have a smaller cluster? Talk to us a little bit about that.
Sure, right. So if you want to be able to have the cluster to fail in place and recover from a host failure, you don't want to send someone to the data center and try to repair a host and bring it back up. Operationally, it's better if you can just let the software recover from the failure. Now, if you have 3 hosts and 1/3 of your capacity is in one host, and you lose that host, then that means that you have to have sufficient capacity on the 2 surviving hosts to store the replicas that were on the failed host. So as each member of the cluster makes up a larger percentage of the total used capacity, the less or the larger your overhead will be in terms of how much excess or how much capacity you need to leave unutilized in order to fail in place from the loss of a node.
Excellent, thanks. So you can see why this as we identify target architectures to base the reference architectures, kind of the classic conversation. When people are new to the concept of Ceph, not obviously after they've been around for a while, but when they're new, they read about these big old 72 bay servers, and they read about the cost efficiency. Then, man, that's exactly what I'm going to do. This software-defined storage, I love this stuff. I can choose any platform I want. I'm just going to go get all 72 bay servers. But then, as Kyle's explained here, you better have a cluster of a petabyte or 2, because when you cram, let's say you got a 72 bay server with 6 terabyte drives, 6 times 7, you're looking at close to a half a petabyte of raw capacity in a single chassis. So clearly this becomes a significant consideration as we identify different architectures. That's number 5. Now, number 6, and I'm going to tee this up for Kyle as well here. So data protection schemes. One of the statements we made at the bottom here is one of the biggest choices affecting the TCO in the entire solution. So talk to us. And it's obviously it's meant to be a blatant attention getter here. You've all been part of conversations with with management or with salespeople, and they say, oh yeah, that's just a detail. You know, don't let's not trouble with that detail. Well, it's actually, you know, do you want to spend half as much or twice as much? Obviously, because the quantity of media that you need is heavily impacted by choice. So Kyle, talk us through the choices of replication, erasure coding. I think we've teed it up here. Just kind of talk to us a little bit about replication, erasure coding, their design, and just what points you want to cover on this point here.
Sure. So the basics, replication is just making copies of each data. So in Ceph, because it's based on Rados, and everything is being stored as an object internally. For each object, there's going to be n number of replicas. Typically, people are using 3x replication, and so as such, you have 1/3 of usable to raw capacity. Erasure coding, on the other hand, uses math to generate parity bits such that you take an object that would be written into the cluster, and you divide that into a number of chunks, and then you also generate an additional number of parity chunks. Both of these can be configurable, and then all of these different chunks, both the ones from the original object and the parity chunks, are then distributed across the cluster according to the crush mapping. And so in this way, if you lose one of those chunks can be reconstituted from the parity, or if in the case of loss of parity bits, they can be recalculated from the original chunks. So this is very similar to like what a traditional RAID array uses internally, except instead of striping chunks across disks, we're striping them across OSDs, and we're using crush to enable advanced placement of these chunks, such that you have one in each host and enough in different hosts so that you can reconstitute them despite the loss of a host or an OSD. As you can see by the quick figure that Brent has on the slide here, is that you end up being able to utilize a lot more of or your usable capacity in relation to your raw capacity is much higher, making it much more efficient in terms of the cost that it is incurred to store data. In some cases, though, the data protection scheme is going to be predicated on the way that you are accessing said data. So in the case of block storage, for example, replication is the only mode that is supported, and that's because since a block device is striped across many objects, sometimes segments of that block storage will need to be updated, and that requires that an object be mutable. In the case of erasure coding, objects are immutable, and so you can't have block storage directly on top of erasure coding.
Yeah, thanks, Kyle. Good stuff. So those 6 design considerations then yield a 4x3 matrix like this. So this is how we go into these reference architectures with one of these empty, and we say we want to work through a variety of different permutations of server, media, and network to identify optimized configurations. And again, I mean, it's one of the reasons why we listed the criteria for how we define optimized. Clearly, every environment is some mix of these different types of workloads, but at least it provides a way to frame the conversation, to say, okay, here's a particular configuration that's for instance, for larger cluster slices, which would frequently tends towards higher density servers. and its particular configuration with network and media lends itself well towards either throughput or IOPS or cost capacity optimization. One of the things to note here, for cost capacity optimized configs and how we approach the benchmarking for these reference architectures for that row, for cost capacity optimized, and we stay true to the criteria, which is, as we discussed above, cost capacity optimized. So, for example, we use erasure coding for the cost capacity, the cheap and deep. So, classic use case of Object Archive. So, for those architectures that we benchmark, they're erasure coded, and they don't use flash write journals because that adds a significant element. And so the cost, again, that's the objective for that row. The cost drops dramatically between throughput optimized clusters and cost capacity optimized clusters. When you can, back to the last thing that Kyle covered, the data protection scheme. When you have, for instance, 73% usable to raw capacity versus 33%, if you need a petabyte of usable storage, instead of buying 3 petabytes of raw in order to get a petabyte of usable, you're buying, more like, 1.4 petabytes. So already that's a tremendous difference in the cost. And then on top of that, when you eliminate the dedicated SSD write journal, just co-locate your journal on your spinners. So anyway, we've stayed true. The configurations that we benchmark for cost capacity in those reference architectures are true to the objectives there in that fashion. So this is the 4x3 matrix. The one on the left we've labeled OpenStack Starter. A lot of folks looking, as they do initial pilots and proofs of concept with OpenStack, they might be using relatively small amounts of capacity, a glance image store, a little bit of persistent Cinder devices and whatnot. So that's kind of, but for the other ones, we've said, okay, small starts at a half a petabyte, medium. Oh, look at that typo there. Under medium, is that 1 petaterabyte? What is that? It's meant to be 1 petabyte, so need to strike the T out of that, or large. Okay. So now it looks like we will have some time just to, so this is how we approach the reference architectures. We sit down with our various partners who have been to date been very gracious in loaning gear. Actually, we work quite a bit with Intel on this as well. So part of the gear, of course, is the process. We sit down and say, okay, this is what we're trying to populate. We want to identify. Of course, there are 100 different permutations that we could test. We want to narrow it down to a handful of configurations that theoretically should be optimized, and then we test them and publish the results. So what you're going to see on the next couple of slides are extracts from our recently published Ceph on Supermicro reference architecture. As noted before, of course, we're Red Hat. We work on lots of different platforms. This one just happened to be the most comprehensive one, so we've chosen extracts from that one. These results are based on lab benchmark results from a bunch of different configurations. Okay, so this first one here, again, the full document, the links are in this slide deck, so you can read the full document at your leisure. It's a little over 40 pages long, so lots of graphs. We haven't extracted all the graphs, but we've extracted a few. Okay, so we'll just kind of give an overview of a few of them, just to kind of give you a sense for how to quickly read them. Okay, first is okay, so the axes of this one here. Obviously the x-axis is the object size fed into the load test utility, so ranging from 4K through 64 to close to a meg to 4 meg, and then the y-axis is megabytes per second. And at the top, it's either megabytes. Obviously we have graphs that the megabytes per second aggregate per the entire cluster. But then we, in order to have a little bit of a normalization so we can have a better comparative, then we break that down. Okay, so if you divide the overall cluster throughput by how much throughput on average a server is producing, this one is per server, and then we further normalize it down to OSD, so we can get a comparative measure, because clusters are different. We benchmark clusters of different sizes. We benchmark chassis of different sizes, and different quantities of OSDs per node. And but the least common denominator for making a direct comparison, of course, is amount of performance per OSD. So in the title, that will indicate what we're looking at here. This one happens to be a 3x replicated pool. It's using Rados bench, so it's coming through at the librados level, not going through, in this case, this study is not going through Rados block device or RGW. And then the lines. So what are the lines? How to interpret the shorthand notation there on the lines. Generally speaking, the first number is quantity of hard drives, OSDs, per server chassis, or per server, I should say. And so the top line is 12. That's 12 OSDs. Plus one is plus one dedicated flash write journal. So, for instance, going down to the green line, 36 plus 2 would be 36 OSDs per server, plus 2 dedicated flash write journals. And in the reference architecture, that it goes into more detail, like those 2 happen to be PCIe NVMe flash, not standard SAS SATA SSD. And then the networking is 10 gig plus 10 gig. That's front and back facing 10 gig networks. So we followed our nomenclature through all of these graphs, except for one exception. 0 plus 2. You'd say, well, that doesn't make any sense. How could I have 0 OSDs and only write journals? Well, it's kind of we kind of didn't stay true to the nomenclature. What it was is, and since we've modified the nomenclature to make more sense, but it's 2 NVMe flash devices running OSDs, also co-located journals. So it's 2 OSDs. So that's the light blue one, the 0 plus 2. That's how you understand that. Everything else is follows the standard. Okay, so looking at the lines. So what observations? Okay, so one might observe that, okay, the good old tried and true 12 plus 12 bay server is the turquoise line. It's what's yielding per server under the 10 gig network saturation point, which is what, about 1100 megabytes per second, somewhere in there. So just under the network saturation point. And then you see on top of that a couple of them per server hitting that network saturation point. And then you begin to see the ones above that that are going beyond the 10 gig network saturation point because they're on 40 gig. In this case, they were using Mellanox Connect X3 40 gig cards. And that's in the reference architectures you read. Okay, so you say, wow, that's pretty sweet. That the pink line, 60 plus 12 on 40 gig. Wow, I'm getting like what is that? 2.5, 3 times more work done per server than I am on the 12 bay. Okay, cool. Now check this out. If you look at the same graph, but instead of per server, if you look at how much work you're getting done, how much value are you getting out of an individual OSD. So the graph almost flips. The amount of work that you're getting done per OSD on the lowly 12 bay is now 75 megabytes per second, versus the pink one is now down around 38, something like that. Okay, so 2 points to take away from this slide. The first is it's really interesting. It's really useful to look not only at the performance per server, but also look at performance per individual OSD because it's the greatest unit of cost, actually. So that's point one. It's useful to look at both. Point two is, hey, I mean, this is benchmarking, reference architecture. It's always, we're always learning new things and having new configurations. So as we spend a lot of time actually with a variety of different performance teams, including Mark, who I think gave last month's talk on here. Kyle and I chatting with Mark about what is the throttle? Why is the pink line not able to get as much work done per OSD as more scarce servers? So consider this as a snapshot in time. I expect we'll probably make progress in figuring this out. And in fact, we've already seen some preliminary results in unpublished studies that where this goes up. But anyway, so a couple different takeaways here. Kyle, anything you want to add on this one?
No, not particularly.
Okay. So then, of course, you can look at it writes. Okay, so here's a softball one for Kyle. So if you look at, so we've stayed with per OSD here. Again, we're looking at a variety of different configurations. You can see that, hey, reference architecture, that's why we do reference architectures, coming back to the original simple question where people say, hey, love the software-defined storage stuff. It can run on anything. What do you recommend? Well, of course, in this world, as architects, you can never make a blanket recommendation. We can provide benchmarking data to help make decisions, though. And that's, of course, you can see it's, hey, these benchmarks produce a wide range, particularly in this case, if you have large block IOs, there's a pretty big spread here. So architecture matters. So here's a softball one, Kyle. So the previous slide, so just looking at the 12 bay, so if I go up one slide for sequential read throughput, it's 70. The 12 bay, the individual drive was producing 75 megabytes per second of throughput with the largest block size, but that drops all the way from 75 down to around 25 with sequential writes. Why are we only getting about a third of the write throughput per cluster? In this case, it's normalized per OSD. Why is that, Kyle?
I mean, that's simply due to the fact that you're doing triplicate replication. So because you have to make 3 copies of it, you're going to see about 1/3 of the amount of throughput as you would see on writes.
And then talk us through the next slide. Is we shift from the previous graphs were 3x replicated, then we shift in this case to erasure coding. So talk to us about okay, so here you can see that the spread is around from about 6 megabytes per second per drive to around 25 megabytes per second, and that spread then shifts from 10 to around 42. Why has the spread shifted up when we use erasure coding instead of 3x rep?
Why are we seeing increased throughput on erasure coding, or why do we see more variance between the configs with erasure coding?
The former. Why are we seeing, in general, why are we seeing more sequential write throughput per OSD?
I mean, so when you're using a replication and you're writing to disk, in the case of 3x replication, one copy is being written at the primary, and then the primary is then streaming the 2 replicas to the secondaries. So coming out the back end of the cluster network, you have a 2x amplification of traffic, whereas and you're also have the 3x amplification of the actual data being written in platters. With erasure coding, not only are you sending less network over or less data over the network, but you're writing less data to platters. So between those two, you're not going to be. It's unlikely that you're going to be bottlenecked by the back-end network, and also the total amount of data that's being written to disk is less. So throughput will be higher.
Thanks for that. Thanks, Kyle. Okay, so this just kind of gives you a feel for the type of, as we do these reference architectures again, we're looking to identify configurations that are optimized for the criteria we had in that 4x3 matrix. Noticing the clock, we're down to a couple minutes left, so we're going to call it here. There's some other things where we bring in relative price performance, and then in the end, this was the for that particular study, this was that 4x3 matrix. So specific model numbers for that one. Supermicro actually, they produced separate Ceph SKUs for these configurations, and you can kind of see how that works. But and then the reference architecture goes into additional subsystem guidelines like CPU memory, server chassis size, and whatnot. So here are a bunch of the ones, both RefArchs and white papers that have been recently published. Check them out. Sorry, went a little bit long here, didn't allow a great deal of time for Q&A, but Patrick, back over to you, however you want to handle it.
Yeah, that's fine. And if we run over a few minutes or whatever, I'm sure people can stick around. So if anybody has questions, now is the time. Go ahead and type them in the chat or come off mute and ask the question. While we're waiting for people to type their questions in, Brent, one thing that I did want to share was the reference architecture / evolved Ceph brag stuff that we're working on. I think you briefly mentioned it there at the beginning, but maybe you want to talk a little bit more about what we're going there, since it was kind of your, it's kind of becoming your project now with the Liturgia guys.
Oh yeah, yeah. So to answer Patrick's question, I'm going to put up this slide right here. So wouldn't it be cool? I mean, so let's say we're all architects on the phone of some type. Wouldn't it be cool to have like 100 different permutations that you could say, I wonder what happens when I change this parameter or change that parameter, and then be able to see just, I mean, because in 10 seconds you can look at this graph and you can kind of take in, how changing different parts of the architecture affects performance. So if the community were to contribute to this benchmark results library, we would accelerate the quantity of comparables dramatically, and that would be great. We think that would be really helpful. Be interested in feedback on that. So I think that was what Patrick was referring to. Not sure that it exists out there. In fact, the people we're speaking with says not sure it exists out there for any storage, let alone Ceph. It'd be cool. Yeah. Other thing I was going to say on that is one of the things you could say, well, gee, it's back to the good thing about statistics is you can make it say anything you want, kind of thing. Well, one of the ways we're trying to standardize things is we work with Mark Nelson to have him open source the Ceph benchmarking tool. So at least the test harness being used here and cluster setup would be done in a standardized way. So that's one step we've taken to try to get a normalized, to ensure normalized numbers.
Yeah, definitely. And the little piece that I wanted to share on the community side of this is that we are working on building this community collector. Those of you that have been around for a while know that we used to have an idea called Ceph Brag, where you'd be able to submit your cluster details and statistics in an anonymized way, so that we could start seeing which clusters were out there and what things are available. We're doing a little bit of a bit shift on that, and allowing people to submit their performance results and cluster makeup and things like that. And eventually, we're hoping that will be in an interactive format on metrics.ceph.com in such a way that people can start playing with, if I want a throughput optimized cluster with options X, Y, and Z, they can see what other people have done and how they can best get to their endpoint, perhaps with specific hardware even. So that'll be fun to see. In the meantime, we've had a question that came in. Are you only using Rados Bench for performance evaluation? Perhaps you could talk a little bit about the tooling, and you mentioned Mark and the CPT and some standardization stuff, but tell people a little bit about what you're using and how you got to your numbers.
You go ahead and start off on that, Kyle, and then if I have anything to add, I'll add.
Right. So this was kind of our first foray into doing extended testing with a partner, and we wanted to test at the lowest level first. Kind of establish baselines, especially so that we understand throughput, because it also pertains to being able to calculate, recovery, mean time to recovery, and such. And so yes, this first analysis focused only on Rados Bench. We've been, most recently, it's not published yet, but we've been doing extensive testing. The follow-up testing to this has been doing a lot of FIO testing on block storage, both using the librd engine through FIO and an FIO with the AIO engine inside of KVM QEMU virtual machines that have RBD block storage devices attached to them.
Yeah, thanks for that. The only thing I'll add to Kyle's comments there is then on top of that, we've worked with the members of the, it's actually a guy from Percona, the MySQL MariaDB community he's created so CBT is a test harness. You plug in different load test utilities in the test harness. So as Kyle mentioned, within CBT, we've been using Rados Bench and different flavors of FIO for random, for measuring random IO. But this guy from Percona has also added a sysbench, so we can drive sysbench MySQL workload testing from CBT. And so that's part of the unpublished study that Kyle's mentioning there. So load test, Rados Bench, various flavors of FIO, sysbench, and Intel has also been integrating COSBench into CBT. Right now we haven't had the bandwidth to do any studies, CBT-based studies or driven studies with COSBench, but that's another load test utility that's integrated into CBT.
All right, I'm not seeing any other questions. If people have more questions, let us know. Oh, here we go. Are you planning to give recommended configuration options per setup?
So I'll respond and Kyle, if you have anything to add there. So we have some recommendations or guidelines per subsystem on that. So things like I'll scroll down a couple of slides. Things like, for instance, the CPU. We did quite a bit of testing, for instance, with dual socket versus single socket, and didn't see, frankly, for throughput optimized and cost capacity optimized cluster, didn't see a huge difference in that second socket being filled. So there's some considerations like that in there. So individual guidelines, subsystem guidelines. There's a few things in there. I think Kyle called them a very technical term, Kyle's bag of tricks, in terms of the just some of his favorite kernel tunables and Ceph.conf tunables and whatnot. That's also like everything, it's with every release it changes and we learn. But we also put through a few of those things in there as well. Kyle, anything to add there?
Yeah, I mean, I think the biggest thing that we found is that using TuneD and the throughput performance profile tends to do very well for Ceph workloads, at least the benchmarks that we were running here. And then probably the second most important thing is that when you have these machines that have a lot of different devices generating interrupts, to make sure that they're being spread evenly across your processors.
has any other final questions, make sure to throw them in the chat here. Get them sorted. I'm not seeing any other questions though, so thank you, Brent and Kyle. This is another great talk. I'll throw it up on YouTube here once it's done, but otherwise we'll see you guys next month. Follow along on the Ceph Tech Talks page on Ceph.com. We don't have a talk slated in for October yet. We're still looking for something, but definitely keep your eye on November. It will not be on the fourth Thursday as it usually is. It will be on a Tuesday on the 17th. There's going to be a talk about the PostgreSQL on Ceph under Mesos and Aurora with Docker. So all kinds of good stuff crammed into that one. Some container mojo, some Ceph mojo, and some database workloads. So that ought to be a good one. So if nothing else, we'll see you guys in October and then again in November. Thanks everybody for coming.